Hey everyone! Today we'll try to minimize the ridge regression's loss function. Firstly, let's recap regularization a little bit. Why regularization? Yes, of course, to conquer overfitting. But we can view this question from a different point. Okay, let's have a look at the loss function first. It's a function of W. L of W equals to summation of I equals to 1 through M over W trans xi minus yi squared. By minimizing this function, we will get the optimal W. It has a closed form solution W hat equals to x transpose x inversed and then W transpose y. Here we have to get the inverse of x transpose x. X is M by N matrix. Ideally, M should be much more larger than N. But sometimes we don't have that much sample. Sometimes M is relatively small. And meanwhile, maybe you have a very high dimensional feature space. It turns out N is bigger than M. Or even worse, N is much more bigger than M. And mathematically, it means X transpose X is uninvertible. For practicing, it means overfitting. To solve overfitting, commonly we have three different strategies. First, we can try to get more data. Second, we can do dimension reducing. And the third one is regularization. Regularization can help solve both uninvertible problem and overfitting problem. We know that W is from a n-dimensional vector space. Essentially, regularization can be viewed as a constraint of this width space. Let's write out the modified loss function. After applying regularization term, it's L of W plus lambda G of W. L of W is the original loss function. Lambda here, it's a hyperparameter you have to tune for your specific problem. G of W here is a penalty term. G of W depends on which regularization strategy we're using. For linear regression, we have two different options, L1 and L2. For L1 regularization, G of W will be 1 norm of W. For L2, G of W will be 2 norm of W. Linear regression with L1, also called Lasso regression. Linear regression with L2, is also called ridge regression. We will focus on ridge regression this video. That's to say, our goal is to find the optimal W, which will minimize this function L of W plus lambda G of W, which should be 2 norm of W. We will call this regularized loss function or new loss function. Next, I will rewrite this function. I'll give it a new name, G of W. What I want to do next is to rewrite it in matrix form. The first term should be W transpose x1 minus y1, and then W transpose x2 minus y2, dot 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 dot. W transpose xm minus ym, and then its transpose. W transpose x1 minus y1, W transpose x2 minus y2, dot dot dot. And the last one is W transpose xm minus ym. They're each other's transpose. And then I will leave the penalty term here. We will take care of it later. Let's look at the first portion. It can be written as this row vector minus another row vector, which is composed with y1, y2, dot 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 dot, ym. It should be m here. Okay. Now they're equivalent, right? It's a row vector minus another row vector. And as every element has a W transpose, we can pull it out. This is okay, right? And then minus y1, y2, dot dot dot, all the way to ym. Now let's look at this part. What's this? This is X transpose, right? It's a feature matrix, M by N matrix. And what's this part? This is Y transpose, right? Sorry, it's not. It should be. It should be N by M. And this Y transpose, it's N by 1, right? Yes. And then we can rewrite them as W transpose X transpose minus Y transpose, right? But this is only the first part, this part, right? We should add its transpose, right? W transpose X transpose minus Y transpose and transpose. And don't forget the penalty term, which is lambda W transpose W. This term is from here, from this term. Let me make it neat. This one doesn't change. This part, it's a transpose, so it should be written like XW. X and W switch their position according to linear algebra, minus Y. And then plus lambda W transpose W. Now we can expand the first term. It should be W transpose X W minus Y transpose X W minus W transpose X transpose Y and plus Y transpose Y and lambda W transpose W. Let's have a look at this term and this term. They're real numbers. And then they're each other's transpose, right? So they're identical. I can cancel one of them and plug in a 2 here. Then it equals to W transpose X W. But this time I want to move this term forward. Move it here. And minus 2 times W transpose X transpose Y. Now let's have a look at this term. As lambda is a constant, I can plug it inside. Then it becomes W transpose lambda W. And I can also plug in an identity matrix here, right? I do this because I want them to be similar, to be with the same form. Now I can write this function like W transpose X plus lambda identity matrix and W minus 2 times W transpose X transpose Y. And then we'll optimize this function by taking partial derivatives. Partial G of W partial W equals 2 is 2 times X transpose X plus lambda I W minus 2 times X transpose Y. We set it to 0 and then solve this equation. We cancel 2 and then X transpose X plus lambda I W equals to X transpose Y. So W should be X transpose X plus lambda I inversed and X transpose Y. Problem is solved. But let's look at these terms. This is a symmetric matrix. It's positive, semi-definite. And this term, as lambda is a positive constant, so it's a positive definite matrix. Then adding them together, we get a positive definite matrix. That means it's invertible. So we can get this closed form solution. So this is ridge regression solution in closed form. And we'll talk about regularization next time from a Bayesian's viewpoint. See you next time.